Alright, hello everybody. Today we are going to be taking a look at another tree problem. This one's problem, it's going to be called the lowest common ancestor. The lowest common ancestor problem is a classic algorithm problem in tree data structures. Given a binary tree and two nodes P and Q, the goal is to find their lowest or deepest common ancestor in the tree. So, to understand better what this problem is going to be asking for, I'm going to switch over to the whiteboard. We're just going to draw out a sample tree to start off with. So let's start drawing a sample binary tree. I remember the last time we did a tree problem, I talked about a binary search tree. A binary search tree is defined by every node. Each subtree to the left of a certain node is going to be less than, and every right subtree is going to be greater than. Each value is going to be greater than the current node. This is just a binary tree, so there's nothing like that. So we're just going to take a look and create some random tree node. So let's start by saying 3, 5, 1. So you see it's kind of random here. 6. Then 0, and then 8. So it was a bit messy, but you got the idea that it's basically, this is something of how a binary tree would look like. Oops. Basically, what this question is asking for, if we're let's go back to the question real quick. Given a binary node, we're given two nodes P and Q. The goal is to find their lowest common ancestor. So what that means is, for example, if we set P to be this value, so let's say this is P, and then this is going to be Q, P and Q, then their lowest common ancestor would be this, 1. Because P and Q both have this exact same parent. 3, they also have the exact same parent, but if we're talking about the lowest one that they have, it's going to be this 1. So if this was P and Q, this would be the ancestor. We can keep going and say, well, what if Q was the ancestor of P? Like, let's say, what if this was Q? Then what's their ancestor? Their common ancestor would just simply be 1, because the lowest common ancestor can include the node itself that it's in. So 1 is the ancestor of P, and it's also the ancestor of itself, is what we consider for the purposes of this problem. And hopefully by now you kind of get the idea of how this entire thing works. If this was P and this one's Q, then the lowest common ancestor would be this. If this one was it, if this was the ancestor P and this is Q, this is the common ancestor, and so on and so forth. Hopefully you got the idea of what exactly we're trying to find in this problem. So now, how will we go about approaching this? Well, one thing to keep in mind is that essentially whatever the problem solving method for this, right, is that what we see is that each ancestor has its own separate left subtree and its right subtree. So there's for example, for this node 3, there's going to be a left subtree and a right subtree. So when we see the value of P and Q, let's say P is in this the subtree and Q is in this subtree, we know that if this P exists in here and Q exists in here, that this is going to be the common ancestor. And that trend will continue. So for a node like 5, for example, let me go like this. For a node of 5, it has the node of 5 has its own subtrees, 6 and so if we know that P is in this subtree and Q is in this subtree, we know that the common ancestor is this. So that's the method of how we're going to be doing this. Basically, we're going to be recursively finding the left subtree and a right subtree of a particular node. We'll starting from the root. We're going to be checking to see if the root is one of those two, the P or Q values. If it is, we're just going to be returning that. Otherwise, we're going to be recursively looking into the left subtree and the right subtree to find P and Q. And if we find it, we're just going to be returning the root. So that's kind of the methodology we're going to be doing. Hopefully you guys got the idea for that. And let's switch to the code and see how this would look like. So as you guys probably noticed, I already started by defining what the tree node would look like. As per our last problem, you might have noticed there's going to be a value, and there's going to be a left pointer and then a right pointer for the two edges for both the nodes that it connects to. So let's start by making our problem def lowest, I'll just say LCA for simplicity's sake. And we're going to be taking a root, we're going to be taking P, and then we're going to be taking Q. And then we're going to be outputting a tree node. Obviously you can just take root out of this condition, because for example the problem might be just asking for P and Q, but for simplicity's sake, let's just say we include the root here as well. So now what's the basic situation? What the basic situation, as I mentioned, well, first, if the root doesn't exist, or if the root is equal to P, or root is equal to Q. So ignoring the first situation, if not root, then it would just be returning none anyways, right? But that does appear in some situations, right? However, here P and Q, as we mentioned in the problem, like for example, if 3 was P and one of the other Q was somewhere else or here and there, all we need, we don't even need to know where Q is. If we see that P is this value, we automatically know that this is the lowest common ancestor. So we're going to be starting by saying if not root or root is equal to P or root is equal to Q, we're just going to be returning the root. So now what we're going to be doing is, like I mentioned, we're going to be searching the left and right subtrees of the root. So we're going to be doing this recursively. So we're just going to call LCA of root.left P comma Q, and right is equal to LCA of root.right P comma Q. So if you saw what I did there, basically root.left is treating the left value as the root, and root.right is treating the right value of the root. And that's how you get the two separate subtrees as we indicated previously. You can look at the whiteboard. This is how we're getting the left subtree and the right subtree, by doing root.right and root.left. Now, what do we need to know? What we need to know is that if, for example, in this function here, if not root, that means that the root is going to be none, right? So if the root is none for every single thing in the left subtree and everything is in the right subtree, then we just ignore it. However, let's say that they're not none, okay? So in any case, let's say left returns something and right returns something. If left returns something and right returns something, then what we know is that if left and right, we're just going to be returning the root. Because if we know that the left subtree has P and the right subtree does have Q, or vice versa, if the left subtree had Q and the right subtree had P, if we know that's true, then the lowest common ancestor is going to be the root value. However, let's say one of the subtrees doesn't have the P or Q that we're looking for. Then we know that all we need to do is focus not on this the left subtree and the right subtree, but only whichever one has the non-null child. So the way we could do this in Python is we're going to say return left if left, else right. So that's a little bit confusing, but essentially what this means is that it's going to be returning whichever one doesn't result in none. So for example, this is where, like, just to recap the previous one, left and right, it means that P is in one, Q is in the other, or vice versa. However, this one, it means that P and Q are both only in one. So we're going to be trying to return which one is that one. And to see that, we'll be returning the left subtree if P and Q are in the left subtree, but if P and Q are both in the right subtree, then we're just going to be returning right. And all of this is just going to be returning that single node, which is going to be the least common ancestor. So yeah, hopefully you guys somewhat understand that explanation. And now I'm going to be, we're going to be testing this code. So if you see over here, this is going to be the visual representation of, I'm just copying pasting, of the thing that I just drew, which is going to be the value of whatever node, of the whatever ancestor node we're seeing. So in this case, P is root.left. We defined it as the value of 5, and root.right is going to be the value of 1. So P and Q, those are the values. When we print this out, what we will expect is we're going to be expecting the value of the common ancestor of 5 and 1, which is going to be 3. So when we run this code, we should expect the value to be 3. So let's run the code. And I'm getting an error message. And yeah, there we go. We got the value of 3 there. And yeah, that's pretty much it. That was how the code was in action. We can take a look to see root dot, could do root dot right dot left, and then root dot right dot right. So this is between 0 and 8. And if we see on the whiteboard, the common ancestor of 0 and 8 is going to be 1. So, I erased it by accident, but you see 0 and 8, it's going to be 1. So we should expect in the code here that 0 and 8 should result in the code printing out 1, and that's exactly what it does. So yeah, the code works like that, and hopefully you guys understood my explanation. I went a little bit over this time, so I'm gonna have to cut out a little bit, so hope you guys enjoyed it. See ya.